Welcome to another episode of learning. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem from the section Linear Algebra that has appeared in the CSIR National Eligibility Test held in the month of December on 15th, 2019. This question is related to the unitary operators, self-adjoint operators, and normal operators. This question is placed in part C, which is a multiple select question. There can be more than one answer, and the question carries 4.75 marks. The question ID is 187-980-1816. This question is suitable for all these examinations. Right. The given question is, let X be a finite dimensional inner product space over C. X is a finite dimensional inner product space over the field of complex numbers. Let T be any linear transformation from X to X. That is, T is a linear operator on X. Then which of the following statements are true? We are given four options. Option 1. T is unitary implies T is self-adjoint. Option 2. T is self-adjoint implies T is normal. Option 3. T is unitary implies T is normal. Option 4. T is normal implies T is unitary. Let's now discuss the solution of the problem in detail. We are given capital X, a finite dimensional inner product space over C, and T be a linear operator on X. Let's now recall the definitions of adjoint of an operator, self-adjoint, unitary, and normal operators. The adjoint of an operator T is denoted by T star, and it is defined as the inner product of Tx, y is equal to the inner product of x, T star y for all xy belongs to X. Such a T star is called the adjoint of T. Self-adjoint operator. An operator T is self-adjoint or sometimes called Hermitian if T star is equal to T. Unitary operator. T is unitary if T star is equal to T star T is equal to identity, where T star is the adjoint of T. Yes. Normal operator. T is normal if T star T is equal to T star. Right. Having known all these definitions, let's get into the question. Right. We first take the option 1. When T is unitary, can it be that T is self-adjoint? It's not necessary. If we think of a counter example, let T is equal to 0 Yeah, you are allowed because it's a inner product space over this field of complex numbers. And when I am writing T is equal to the matrix 0, I 0, we mean that the matrix associated with the operator T, the matrix representation, is this one. That's the meaning. It's not otherwise a linear transformation is equal to matrix is not there in the literature. Right? We take T is equal to a matrix means the matrix associated with T with respect to a set of with respect to a basis is this matrix. Yes, that is the understanding. Then T star in matrices star adjoint is transpose of the conjugate or conjugate of the transpose. T bar transpose. That is 0, 0, minus I, minus I, 0. Take the transpose again, you will get 0, minus I, 0. First take the transpose, 0, minus I, 0. Then take the transpose, then it will be 0, minus I, 0. Agreed. Now, TT star is write the matrix 0, I 0 and its adjoint. So this is the one. That is the conjugate in this case. That is equal to identity. When multiply, simple multiplication, identity. And you also see T star T is also identity. Check. Right. So here is a matrix. And I have shown you TT star is equal to T star T is equal to identity. That means T is unitary. But is T self-adjoint? Is Hermitian? Is T is equal to T star? No. T is not self-adjoint since T star is different from T. Thus, T is unitary not necessarily imply T is self-adjoint. Agreed. So, option 1 is not true. Get into the... And one may say, sir, why this complex matrix? Why not we take a real matrix? A real matrix is also a complex matrix. This also works now. Why not we take this? Yes, you take it. But I have shown you there is a complex matrix just to say that it is an inner product space over C. Therefore, why not I try a complex matrix? Otherwise, you can do it. This is as well good. Now, option 2. T is self-adjoint implies T is normal. Yes, every self-adjoint operator is normal. How do you show? T is self-adjoint, that is, T is equal to T star Hermitian. Now, to show you TT star, to show you it is normal, I have to show you T star T is equal to TT star. So, T star T is equal to, for the first T star, T into T. Now, TT, you write T into, for the second T, you write T star. So, T star T is equal to T star, therefore, T is normal. T is normal. So, every self-adjoint operator is normal. Option 2 is true. We continue the discussion in the next slide. Option 3. T is unitary implies T is normal. Every unitary operator is normal. Is it so? Yeah, T is unitary implies TT star equal to T star T is equal to identity. Anyway, this satisfies TT star is equal to T star T, therefore T is normal. So this implies TT star is equal to T star T, T is normal. T is normal. Every unitary operator is a normal operator, therefore option 3 is true. Go to the option 4. T is normal implies T is unitary, not necessary. Give a counter example. Let T is equal to 2003. Then T star is T bar and its transpose is again 2003. Take the bar conjugates, they remain the same because they are real numbers. Then take the transpose. Transpose is also same matrix because it is a diagonal matrix. Now TT star is, when you multiply, this is 4009, and also say T star T is also 4009. Right. Thus, TT star is equal to T star T is equal to 4009. They are equal. That is sufficient for us for the normality. Therefore, T is normal. Therefore, T is normal. Is T unitary? No. Why? TT star equal to T star T is equal to 4009, which is not equal to identity. To be unitary, T star T is equal to T star, it must be equal to identity, but it is not. Therefore, T is not unitary. So, T is normal, not necessarily will not imply T is unitary. Therefore, option 4 is not true. Combining all the options, the answer, and yes. You may try a complex matrix like this also instead of 2003. You do it, check. So take it and do it. And the answer to this question is options 2 and 3. That is the detailed discussion of the solution of this problem. And if you know the property, if you know the definitions of the normal operator, self-adjoint operator, a unitary operator, then it comes out very easily. For the remaining, for the counter examples, you have to think a little bit, but not much. Then you will get them also. Right. So I have added a note here. What's the note? Let X be a finite dimensional inner product space over the complex field. Let X be a linear operator. We have seen that every self-adjoint operator is normal and every unitary operator is normal. These two are implying they are normal operators. Note that. So one is interested in asking you, a normal operator is not necessarily a self-adjoint and unitary operator. This is what is wanted. We want to show a normal operator, when you go in a reverse manner, is not necessarily self-adjoint or unitary. For that, you have to give a counter example. So, example, T is equal to 2 minus 1, 1, 2. Take its T star, T bar transpose is 2, 1, minus 1, 2. Yeah. This is right. Just transpose because the conjugate will not work here because these are all real matrices, right? Now, it is not self-adjoint because T is not equal to T star. Yes, T is not equal to T star. Now, TT star is T 2 minus 1, 1, 2 multiplied by T star T1 minus 1, 2 multiply. You will get 5 times identity. And T star T is also 5 times identity. Check. So, T is not unitary since TT star is equal to T star T is equal to 5005, which is not equal to identity. So, it is not unitary. So, this is an example of and it is normal. It is a normal operator because T star is equal to T star T is satisfied. So, thus A is a normal operator is not necessarily self-adjoint or unitary. The T what you have taken is a normal operator, which you can see is here TT star is equal to T star T. That much is sufficient for you. So a normal operator is not necessarily self-adjoint or unitary. Yeah, this is worth noting. And as I've been advising you, whenever you see a problem, what are the concepts and theorems that you have used or seen in the question. So in this question, there is So what is an adjoint operator? What is a self-adjoint operator? What is a normal operator? What is a unitary operator? How are they related? And the homework to you is, what are the properties of self-adjoint operator, unitary operator, normal operators? Like what are their eigenvalues? What are their eigenvectors? And how eigenvectors, what are the properties of eigenvectors? Is diagonalizability possible? Etc. etc. Such things you study, note down, and make a notes of it. That will be helpful for you. With these few words, I say, I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. I hope that we will meet once again in another episode of learning. Keep learning mathematics and enjoy. I wish you all the best. Thank you.